In this question, we have a rocket-powered sled, which starts speeding up until it reaches a final velocity of 100 meters per second. It does this by accelerating at a rate of 200 meters per second squared. Once the rocket reached the velocity of 100 meters per second, it glided at a constant velocity for 10 seconds. After which, it starts slowing down until it comes to a complete stop in 30 seconds. We are asked, how far did the rocket travel during this entire journey? We will start answering this question by writing down what was given. And because there's different velocities and acceleration throughout this entire journey, we have to break the motion down into 3 separate parts. So for the first part of this motion, we can say that the initial velocity, VI, was 0 meters per second because the rocket hadn't started moving. Then the rocket reaches a final velocity of 100 meters per second. And it does this by accelerating at a rate of 200 meters per second squared. We will call the next part of the motion B. This part of the motion differs from the other parts because the rocket is moving with uniform motion. This means it's moving with a constant velocity, so it's not speeding up or slowing down. The velocity V stays at 100 meters per second, and we were told that it moves with a constant velocity for 10 seconds. The final part of the motion is when the rocket is slowing down, and we will call this C. Within this motion, we have VI, our initial velocity, which is 100 meters per second, and we know VF is 0 meters per second because the rocket comes to a stop. And this slowing down takes 30 seconds. Now, before we move any further, we want to remind ourselves what we're solving for. And we're solving for delta x, the change in the rocket's position. So we will have to calculate delta x for parts A, B, and C, and then add them up. Let's start with part A. In order to figure out what kinematic equations we need to use, we need to ask ourselves, what variable are we missing? Well, we know we're missing delta t. That means we need to use a kinematic equation that does not include delta t. And that equation would be our Vf squared is equal to Vi squared plus 2a delta x equation. And we will use this equation to solve for delta x. Moving on to part B, we know we can use the uniform motion equation, which says that V is equal to delta x divided by delta t. We can simply rearrange for delta x and solve. When we do the math, we find that while the rocket is moving with uniform motion, it travels 1,000 meters. Now let's move on to part C. In order to figure out what kinematic equation we need to use, we have to think, what variable are we missing? And we can see we are missing the acceleration. So we need to use a kinematic equation that does not include acceleration. The only one that does not include acceleration is our delta x is equal to Vi plus Vf divided by 2 times delta t. And we can use this to solve for delta x. And so now that we have the kinematic equations that we need, we can solve this problem. Beginning with the motion in part A, I'll just remind us that our initial velocity was 0 meters per second, our final velocity was 100 meters per second, and our acceleration was 200 meters per second squared. We figured out that we are going to use the Vf squared equals Vi squared plus 2a delta x kinematic equation, and what we need to do is rearrange this equation to isolate for delta x. Once we've rearranged this equation, we can just plug in our values and solve for delta x. And what we find is that our change in position for the first part of the motion is 25 meters. For part B, we had already done the math. We used our uniform motion equation, and we found that the change in position when the rocket moved with a constant velocity was 1,000 meters. Then for part C, which is when the rocket was slowing down, we know the initial velocity was 100 meters per second, the final velocity was 0 meters per second, and it took the rocket 30 seconds to slow down. We figured out that we can use the delta x is equal to Vi plus Vf divided by 2 times delta t equation. And we don't even need to rearrange. All we need to do is plug in our values and solve for delta x. When we do the math, we find that the rocket moved 1,500 meters as it was slowing down. Now all we need to do to solve the question is add up these displacements. So we have 25 meters, 1,000 meters, 1,500 meters, for a total of 2,525 meters, which is how far the rocket traveled throughout this entire journey. Now we can move on to part B, which asks, what was the rocket's acceleration as it slowed down? So this would be part C of our motion. So now on a clean sheet, we'll answer part B. And just remember, we had our rocket moving with a velocity of 100 meters per second, and then within 30 seconds, it slowed down to a complete stop. Remember, initial velocity was 100 meters per second, final velocity was 0 meters per second, and it took 30 seconds. We also just determined delta x, so we know the rocket's change in position throughout this motion. But we don't even need this delta x value. If we just use our VI, VF, and delta t, we can use our kinematic equation, which says VF is equal to VI plus A delta t, and we can rearrange and isolate for our acceleration A and solve. All we have to do is plug in our values, and when we do the math, we find that the rocket was accelerating at a rate of negative 3.3 meters per second squared.